hit the all-important record button. Note to self, please start recording. Okay, that's done. Good deal. So I was going to talk about chi-square this morning, just an introduction to it, but I got to looking at all the grades so far and people's progress and different things, and then also I noticed I hadn't actually posted all the solutions for assignment 6. So what I may do, I may make a video on chi-square, and that's just optional. You can watch it if you've got time and you're interested. It's a very interesting topic, but it's not required for the class. I think it's a good idea that you're introduced to it, but there are no assignments in it. But I may make a video and post it so you guys could watch that. And it's in the book also, section on chi-square, but it expands the scope of statistics beyond things that are immediately obvious that there are numbers associated with them, things that you measure or that have numerical magnitudes already. Those just lend themselves to statistics naturally, but also it turns out that there's a lot of statistics can be done on categorical variables, which are things that don't really necessarily have numbers associated with them at first glance. And for example, just when you think of a category, which is a very general thing, right? That's something we all do all the time. We put things into categories. And when things are in categories, you can count occurrences of things that are in categories. And just by that simple fact, now all of a sudden you can do lots of statistics on different categories of things. And so that really extends the reach of statistics. And then that's just the beginning of categorical analysis in statistics. There's a thing called logistic regression, which we're not going to cover, that gets more involved and more detailed and gives you more insight into statistical properties of categorical variables. And another way to think of categorical variables is qualitative, right? Some things are numerical just naturally. A distance has a number measure for it, or a weight. Any number of things, pardon the pun, but categories can be, colors, red, blue, green, or any kind of trait or characteristic that something has. So that's why chi-square is really a good tool, and it's worth knowing something about. So I'm going to try to, I'm a little bit behind here, getting a lot of things done, but if I get a chance, I'm going to make a video just on chi-square and post it. And again, that's purely optional. So today, I'm going to work the assignment 6 problems and post that. So people that were having trouble with that assignment can maybe look at that assignment again, or understand what the steps are on all the problems, and hopefully that'll instill a little more confidence with people. So let's get started. Let me see. You guys got any questions on anything before I go into this? Okay, I don't hear anything, so I'm going to get started. All right, so this should, I don't want Safari, I want Chrome. There we go. Okay, assignment 6. Question 1. Okay, and you don't see that yet, so you will. Let me have to stop share, restart share, pull this up, reshare. Okay, so you should be able to see that now on your screen. I like to move this stuff around. Too many screens open here. Okay, random sample of 20 colleges was taken. The mean debt after graduation was $17,910 with a margin of error of $1,406. Distribution of debt is normal. Complete A and B. So A says choose the correct interpretation of the confidence interval below and fill in the answers. Okay, so let's go back to the problem. We have a sample here of 20 colleges, and this mean debt that's given here then would be our X bar. Okay, that's our sample mean, 17,910. And we need a 95% confidence interval, okay? Well, in this problem, they gave us the margin of error already, okay? And so the confidence interval is just X bar plus or minus the margin of error. That's what it is. And the margin of error is associated with a particular confidence interval. Now, they don't say that up here, but we have to assume, since this is all we have, that this refers to the 95% confidence interval, okay? Which is typical. That's the one that's probably used the most. So you just subtract 1406 from 17,910 and you get your lower limit, and you add 1406 to 17,910 and you get your upper limit. And then the correct interpretation is that we're 95% confident that the population mean, okay? So confidence intervals are always statements. It's based on a sample. You obtain a sample, and here we're doing means, so the sample's an X bar, but the confidence interval is an estimate about the population parameter. So we're 95% confident that the population mean is in that interval that we calculated. Okay, part B. Can we reject a population mean of 17,320? And so you look at your interval and you ask, is this value inside this interval or not? It is inside the interval. So if this were a proposed population mean, or say a null hypothesis, then we look and we see, is that in this confidence interval we calculated based on our sample? It is in there. Because this is in the interval, we cannot reject this as being the true value of the population mean. We cannot reject it. We can't rule it out. So the interpretation is we do not reject, since it's in the interval. It's plausible that the population mean student debt is that number, okay? A lot of times one of these answers will say it means that the population mean is definitely that value. Well, just because you cannot reject it does not mean that it's definitely that value. It does not mean that at all. It just means that you cannot rule that out. It's plausible, which is possible, or slightly more than possible, that is the value. Okay, let me see if this thing will let me scroll here. We can get to the next part. Okay. All right, so we got a new problem here. I wonder if it'll let me move. I'd like to move this thing. It won't let me move it. Okay. Yeah, I'd like to minimize it. Anyway, the weights of 4 randomly chosen bags of horse carrots. They're labeled 20, so the bags are labeled 20 pounds. So this is the nominal value or this would be our null hypothesis value, okay, if we were going to do a statistical test. This is the claimed value, 20 pounds. Well, here's our sample, and we want to note, well, how large is our sample size? It's 4. We got 4 data points that make up 1 X bar, okay? Assume the distribution of the weights is normal. Therefore, we know we can use the central limit theorem. Find a 95% confidence interval for the mean weight of all bags of horse carrots. Okay, so how do we do that? Let me switch the camera here, if I can. I'm going to show you. Yeah, go to this. Okay. Get that message off there. Yeah, I had this set up pretty well, I thought, but I don't like the way it's there. And it focuses better, I think, if you do that. Yes, that's a better focus than autofocus. Okay, so our null value for the mean is 20. We got 4 data points in our sample, and it wants us to calculate a 95% confidence interval, okay? So to get our confidence interval, what you do is you get X bar, which is just the mean value for your sample, right? And then plus or minus the critical statistic, okay? And what is the critical statistic? So for one thing, it's going to be a statistic that comes from the fact that we're using a 95% interval, right? If you change this value, this changes this statistic. I think hopefully we understand that now. The other thing to note is I've already written T here, but so the general formula is X bar plus or minus the critical statistic. So you have to ask yourself, well, what critical statistic are we talking about? And what I mean by that is you have to choose between, are we using a Z distribution or a T distribution in order to calculate that, okay? And I put out a thing earlier in the class a couple times now that says, that choice, whether you're using T or Z, depends on, for the most part, your sample size, okay? If your population is normal and you have a large sample size, n greater than 25, you use Z. Population normal, small sample size, n less than 25, you're going to use a T distribution, okay? Let's see. If your population's not normal, but you have a large sample size, you can still use a T distribution. So it's very versatile, the T is, okay? And then finally, if your population is not normal and your sample size is small, you're out of luck. You can't do any of these central limit theorem statistics. But in our case, it told us that our population was normal in the problem. And so we note our sample size, it's small, n is less than 25. So we know we're using the T distribution, okay? So we get this value for T star. T star is going to depend on 2 things, right? It's going to depend on what confidence level you're talking about. And here we have a 95% one. The other thing that determines T star is the degrees of freedom, which again comes from your sample size, right? Degrees of freedom is n minus 1, okay? So that's pretty easy. We know our degrees of freedom is 3. This determines which T curve we're looking at, okay? That's what degrees of freedom does for us. There are many different T curves. This tells you which T curve you're using, okay? And then the confidence level tells you where on that curve that T is located, and that's the value T star. So let's go to Statcrunch and get that. Oh, well, back up 1 second. So 95% confidence intervals, X bar plus or minus your critical statistic. And for this problem, we see that's going to be a T statistic. So T star times the standard error. The standard error for means is the sample standard deviation divided by the sample, the square root of the sample size, n. But let's go to Statcrunch now. I got to do a lot of stop, share, reshare stuff to get back to it. Share screen. Here's Statcrunch. Share. So why didn't, let's see, if I click down there, nice. Okay, couple things to look at here. Ignore this report for a second, okay? Well, we'll ignore all of it. We'll do it all again here. Here's our sample data, okay? We want to know what T star is. There's two ways of doing this in Statcrunch, okay? One way is, well, I'll show you the faster way first, okay, is we can do this T-stats, and this will give us our confidence interval very quickly, okay? So we select stat, T-stats, one sample, because we have 4 X's, but they make up 1 X bar, right? But we actually have the data that makes up that X bar. So we say one sample with data. We select the data. And then we can just jump straight down here and click confidence interval. And you can notice you can type in whatever confidence interval you want. We want a 95% one. And you're done here. You hit compute. This gives you your confidence interval. 19.4205 is your lower limit. 20.7295 is your upper limit. It gives you other information about your sample mean. Here's X bar, and it gives you what the standard error is. So we didn't have to calculate standard error and the degrees of freedom. So that's a real nice report. And that whole thing came just from saying stat, T-stats, one sample, and either you have data or you don't. You just have summary information, and then you select the column of data or put the summary information in, you're done. It gives you this report. So that's nice. Okay, but in some problems, maybe you don't need all this, but you may need to know just to work out something else. You might need to know, what is our T star? What's the value of T that we're going to compare our test statistic T? That's the T value you get for your sample. What's the critical value of T that we're going to use to compare with our sample, the T value we get for our sample? So to get what a critical value of T or T star, you can go stat, calculators, come down here to where it says T, right? So calculators T. Okay, this is a confidence interval thing. So we know it's a two-tailed test, if you will. So we have to check the between option. So we get 2 values. So these values down here are going to be our critical T values. This will be plus T star essentially, and this will be the same value, but it'll be negative. So this is our critical T. It defines what the rejection regions are going to be, which are the tails of this, right? That's what T star does for you. Z star does the same thing. But here we're using a T distribution. So remember I said the degrees of freedom determine which curve you're using. So just notice this, what we've got here already, just the general shape of it. If you change this degrees of freedom, okay, our sample size was 4, so our degrees of freedom is 3. And these aren't the actual numbers we're using for this problem. I'm just plugging this in just to show you that see where this curve radically changed, and all we did was change the degrees of freedom. So each degree of freedom has its own T curve, right? And that shape is completely specified. The shape just by the degrees of freedom. So that's important to note. But now to solve our problem, we were calculating a 95% confidence interval. Okay, now we did have a degrees of freedom of 3, for our problem. So here we just need to put in the confidence level we want, which is 0.95, and we hit enter. Now, because this thing is a t calculator, down here where it says x, this is actually t. Okay, so this says that the probability, if you do a random sample from this distribution using a sample size of 4, which is degrees of freedom of 3, there's a 95% probability that your sample is going to land between these two t values, okay? So these are the t star values, if you will, plus t star and minus t star, that would be used on a statistical test. And then the test would be your sample has a t value associated with it, right? So you compare that sample t with this t to decide if you're going to reject the null hypothesis or not. So you would get your sample. This is the probability distribution for this t at 95% confidence. These are the critical values, the end of this red region. So if your sample falls outside of that region, you'd be rejecting the null. If it fell inside, you would not reject the null. But anyway, this P is the probability that this thing in here, which is actually a t value. So the probability that your sample t is between these two values is 0.95. And these two values are your critical t values, okay? So t star is 3.1824, and negative t star would be negative 3.1824. And also remember from this scale, so this is t, but this is also, if you put the actual numbers in here, in this case it was weight for bags of carrots, weight of carrot bags, then this would also be x values across here. But this thing right now is giving us the t units for the sample, okay? If we want, we could do this in x units, but then we'd have to change the scale. And so anyway, we've got what we needed. This is where you get t star. This is one way you can get t star. I put a thing on Blackboard that tells you how you can get t star from a Texas Instruments calculator really quick. There's a little short video that tells you how to get t star that way. But this would give you t star. So getting back here, how do I get back to, let's go here. What's this? Show. Yeah, I'm having trouble getting back. Oh, I have to stop share. That's what it is there. Okay. So getting back to this, we calculated what this t star value was. We could calculate what the standard error is very easily. We just get the standard deviation of our sample. And this is a calculation, either the calculator or computer. You plug these numbers in. You could do it by hand, but it's very tedious, right? It's a lot of steps in a lot of numbers in the formula. But anyway, sample standard deviation divided by the square root of the sample size is 4. It gives you the standard error. So the confidence interval for means is just x bar plus or minus critical statistic. And for this one, since we had a small sample size, we're using a t statistic times the standard error, okay? So you could do each one of these with a calculator if you wanted, or we could run that report that we ran before. So let's go back to the problem. If I can get back to it, let's see if that's what we want there. Why didn't it? Let's well, it does that. It goes to the wrong. Okay. Was that? That was question 2, I believe. It won't stay on it there. Okay. Now I got to stop share and reshare. I've had this up twice, so hopefully. Yeah, I don't know why it doesn't go back. I open the problem up and then it doesn't go to that screen. Yeah, that's stop sharing, start sharing. Okay. This is the problem. Now, finally, okay, I got back. All right, so we calculated a confidence interval, okay, and then says, can you reject a population mean of 20 pounds? I think we did that already. Or maybe this was a different problem. Anyway, 20 is in this interval, so we cannot reject it. And since 20 is, okay, so do not reject because it's in the interval we calculated. Since it's in the interval, it is plausible that that is the mean, okay? That's correct. So let's continue here. Maybe that's, okay, another problem. Researcher collects a sample of 6 measurements from a population. Now we want a 90% confidence interval. So that's going to change our Z star or T star, whichever one we end up using. 90% is going to determine the value for that statistic. What value should he use for T star? Okay, he collects a sample of 6 measurements. Okay, so we know we're doing a t distribution here because it's a small sample size. We want to find a 90% confidence level for the population mean. It says, what value do we use for t star? Okay. All we need to know to get T star is sample size and confidence level, and we've got those here. Sample size is 6, so degrees of freedom is going to be 5, and we want a 90% confidence level. So we go into Statcrunch, and I'll have to stop share. Let me go into it, and then maybe, let's see. Okay, I gotta click that. All right. Click that. So I don't know why that it doesn't go to it there for some reason, and I don't know why. Okay, so here's Statcrunch. Why doesn't that pull? It did before and now it doesn't. What's this under here? There. Now, let's say stop share. Share. There. 4th time's a charm. I don't know why. Now it does it. No idea. Okay. We're back to this. So again, we're just determining a T star value here. So you go stat, calculators, and then you choose T, okay? We want a 90% confidence interval, so we know we have to do this between function because we're talking about a critical value on either side of the mean, right? And down here, our sample size was 6, so degrees of freedom is 5. And then we put in our 90% for our probability. 0.90 is a probability, but that's equivalent to 90% confidence interval. We say compute, and here's our new t-star values. Okay, here's positive t-star 2.015 and negative t-star minus 2.015. Okay, I'm gonna write those down because I gotta go. T-star 2.015. All right, let's go back to the problem. Let's see if I can get back to it this way. Let's say stop share, share screen, and try here. Good. Okay, that appears to work. So I got to put the value in that we just calculated. 2.015. How many decimals? It wants 3 decimals. So that's right. 2.015. Okay, it likes that. Okay, a researcher collects a sample of 10 measurements from a population and wants a 99% confidence interval value for t-star. So this is just the same thing, right? This is getting pretty routine now. So we'll go into Statcrunch, stop share. Well, already, I think he said, I think the sample size was 10 there. Was that right? No, that's not, I don't want that one. Actually, I'd like to close that one. That's Safari. I don't want here. There, Google. Okay. I think it's. Oh, we did that one already. Let's go next. Okay, it changed the problem because I went into it again. Let's see if we can get. Yeah, it keeps changing the problem. Okay. Anyway, our sample size is 10 here. Okay, 10 measurements, and now we want a 99% confidence interval. Okay, so we go back to Statcrunch. And it didn't go back to it that time. I don't know why. There. Oh, okay. There it is. Okay. So our sample size is 10. So degrees of freedom is 9 and a 99% confidence interval. So here's our critical T, or T star, for this test, okay, is 3.2498. And I have to say stop share. And we go back. That's Google. Okay. Well, I select on the problem and then it pulls up Statcrunch again. So that's irritating. All right. And now I came back to it and it's got a different problem. I think you get the idea here. I think I'm going to go on here because every time I come back to this screen, it changes the numbers. It thinks I'm entering the problem again. But so we just did the same steps here, right? To find the T-star, you go Statcrunch, calculator, select the T calculator. And if we're talking about confidence intervals, we're going to select the between option. Excuse me. And then you enter your confidence level as a probability in the lower right-hand corner, and enter your degrees of freedom, which is just n minus 1, sample size minus 1. And that gives you the T star you want. So I'm going to see if this will let me continue here. Okay, next problem. A hamburger chain sells large hamburgers. We take a sample of 30 hamburgers. So we notice that the sample size now has changed, right? We're into the large sample category because n is greater than 25. So that will allow a z-test if the population's normal, okay? It says when we take a sample of 30 hamburgers and weigh them, we find the mean value is 0.57 pound, and we have a standard deviation. So it doesn't say anything about the population, whether it's normal or not. So we're going to assume that the population is normal. Because if it's not, well, no, actually, let me take that back. We will not make that assumption because we have the case when the population is not normal, but our sample size is large, meaning more than 25, we can still use the t distribution, okay? So in order to use the z distribution here, we'd have to go out on a limb and make the assumption that the population has a normal distribution. Since we don't know anything about the population here, that's not a safe assumption, right? If you were doing a critical test. So your more conservative, safer assumption is that population may not be normal. Well, if it's not normal, T gives us a more conservative value, okay? And we're allowed to use T if we have a large sample size, which we do. Okay, so we find the mean is 0.57 and the standard deviation is 0.0. Okay, technology input menu for calculating it requires sample size, sample mean, and a sample standard deviation. State how you would fill in these numbers. Okay, sample size, we just fill them in. 30, sample mean. We find that the mean is 0.57 pounds. The standard deviation is 0.1. 0.1, okay. Check answer. We're all right there. Okay. Choose the correct interpretation of the confidence interval, and we have to do a confidence interval, okay? So we've got to use our T statistic, our T star, critical T, to get our confidence interval. So we'll go into Statcrunch, and we know that n equals 30, and we want a 95% interval, okay? But let's write down all this. So our X bar is 0.57, and the standard deviation, so that's S, is 0.1, okay? Now we can go calculate that. We'll just use that shorter method in Statcrunch to get the report that's going to give us the confidence interval. So stop share, reshare. Yeah, see, I selected Statcrunch, but if we go here, oh, okay, and you can see that because it's highlighted. Okay, so let's close this and ignore, this is from an earlier problem, so maybe I should delete it just so you don't, okay. Okay, we don't want any of that. So stat, and now we're going to use t-stats, okay? One sample. And we did not have the individual data. We had the summary information, right? They gave us X bar and what the standard deviation was. They did not give us individual points. Therefore, we use the summary. So t-stats, one sample with summary. Okay, the sample mean was 0.57. The standard deviation, that's of the sample, so that's S, and that's 0.1. And the sample size was 30. And we just want a confidence interval, okay? So we say compute. And here's our confidence interval. 0.5327 for a lower limit and 0.6073 for the upper limit. And the other information we don't really need here. I think it's just asking about the confidence interval. So let me see if I can get back to the problem here. What if I click over on this first and then do stop share, reshare? Not sure if that's maybe question 4 now. It didn't come up. Maybe I have to hit stop share. Okay, and that's Safari. I don't want Safari, I want Google. That's not. Yeah, that's the problem we want, but you can't see it right now. Let's see if it'll let me. Let me get back to where you can see it. Okay, good. All right, this is a little difficult to get these screens to show up where you can see them all the time, but I think we're there on this one. All right, so we just entered our sample information here, and we wanted to calculate a confidence interval, which we wrote down what it was. And it says choose the correct interpretation. So we got to see whether we want A, B, C, or D. So there's a 95, I'm going to read A, there's 95% probability that the recorded sample mean is between such and such. Well, this is wrong because there's no probability that the sample mean is anything. The sample mean is already what it is, right? It's not a probabilistic thing. We know what it is. We go get a sample, we look at it, we know what our mean is. So there's no probability associated with the sample mean. So let's look at B. There's 95% probability that the population mean is between. Okay, now you have to be careful here. And what will keep you out of trouble on these kind of problems is remember, we're always talking about confidence intervals, okay? Now, while they involve probability, just keep that in mind. We're talking about confidence interval. So that's going to be in the answer. It's going to have something to do with confidence, okay? So our answer is going to be C or D because both of these say we're 95% confident. And the reason for that is it's a little bit technical, but when you calculate a confidence interval, what that actually means is this, that if you went out and sampled many, many times, okay, and each time you sample, so each time you get an X bar, you calculate a confidence interval for that, okay? And then you repeat that whole process. You go get another X bar and you calculate the confidence interval that's going to go with that one. And you continue doing that. You do that many times. So the interpretation of this confidence interval is that if you did that whole process many, many times, 95% of the time that you calculated a confidence interval, that interval would in fact contain the true population mean. So it does not mean there's a 95% probability that your interval contains the mean, because the true mean is either in your interval or it's not in your interval. It's not a probability. It is what it is. You don't know what it is necessarily, but it's not a probability of if it's there or not there. But there is a 95% of all these confidence intervals that you would calculate do contain the true mean. So in these answers, they're kind of tricky that way. You want to select the one that talks about confidence, okay? So here we're left with two choices. We're 95% confident. And here again, let's look at D. This was kind of like part A was. It says we're confident that the recorded sample mean is between such and such. Well, no, that's not right. We know what the sample mean is. So we're not a 95% confidence that the sample mean is in some interval. We know exactly what the sample mean is. What the confidence interval pertains to is you're estimating kind of an error bracket around your X bar for where the true population mean may actually be, okay? So we're 95% confident that the population mean is between, and here we'll type in the values we got when we did our interval. So that was, and how many decimals does it want? It says round to 4 places, so 0.5327 and 0.6073, 6073, and we enter, and it like that. Next question. Okay. A random sample of 7 men's resting pulse rates showed a mean of, I'm going to write this down here, 72.2 beats per minute. So that's X bar, right? It's a sample. So X bar equals 72.2. Sample size is 7. N equals 7. And S, the sample standard deviation, is 18.8. Assumed pulses are normally distributed. Okay, so we know we're doing a t-test. Use the table to complete A through C. So here we actually get to look at a t-table. So I got to share this screen with you. Let's read the problem before I go pull the table up. Okay. Find a 95% confidence interval. Choose the correct answer below. Okay, so we could get, so this part A, we're calculating a confidence interval. So we don't have to have this table to do that. We can do that in Statcrunch. Okay, but let's see. So we don't even have to see the table yet, but maybe it'll give us information that'll make it easier to calculate this without going through Statcrunch. The reason that I'm hem-hawing around on this is this thing where I have to share and unshare and share and unshare screens every time I go to one screen and come back to one. So I'm just saying that there are more than one way. There's more than one way you could calculate this confidence, but I'll pull up the table and see if I can share that table with you, okay? So I think I want to say stop share, and then if it'll let me come back to this, share screen. Okay, you double click on that, it lets you come back to it, but it reshared it, and I didn't want to share that. I want to, I don't think, okay. Can you guys see this t-table? Speak up if you would, because I can't see the chat screen where I'm at right now, but I can hear you if you speak. Hello?
I can see the table.
Okay, good deal. Thank you. Okay, so here we have a t-table. All right, and this is nice to look at because we just keep using Statcrunch a lot. It used to be that almost all statistics were done. There are lots of different kinds of statistical tables, okay? And in the past, this is how statistics were carried out. You would go to tables to look up information that you needed, and they worked very well, okay? And so a couple of the basic tables, there's a t-table, and t-tables, and there's a z-table, okay? The z-table, the thing about the z distribution is there is only one z distribution, okay? And it is the standard normal curve. So there's only one true z-table. Now, sometimes, depending on if you're doing a two-tailed test or one-tailed test, they'll present tables in different forms, but they're all coming from the same distribution. Anyway, that's another point. So back to this t-table. All right, so you'll notice here there are two things that you need to know. So what this table does for you, these values that are in the table, okay, the actual values that are in the cells of the table, these values are T star values, okay? Well, well, okay, yeah, that's true. So these are critical T values, okay? And the way this works is you specify which degree of freedom that you're talking about. So that's this first column over here. Okay, now our problem we're doing right now, n was 7, n equals 7. So degrees of freedom is 6. But what this is doing, which I kind of showed you earlier, and you don't see it exactly when you look at the table, but you could recognize it in your mind, is actually each one of these degrees of freedom is selecting a different curve. So each row of values are values from a t distribution, and each one of these is a slightly different t distribution. Each one of these is a different z curve, okay? But the way it works is you just look up your degrees of freedom. That tells you which t curve that you're actually on. And then the value, the critical value of t, is just a function of what confidence level you're interested in testing at, okay? Now, we have something very important here that we haven't talked about much at all in this class, and this is very important. Notice here it says right tail probability, okay? Those are key words in this table. So this table is not, it does not pertain to a two-tailed test per se. This table was set up for a one-tailed test, okay? And so what these critical values of t in this table are, and let's pick one here. I think we were doing the 95% confidence for this problem. Yes, we were. Okay, so we go to 6 degrees of freedom. Then we come across the rows until we get to 95% confidence, which you'll notice up here under confidence level. So it's like the middle column. And actually, I take that back, what I said about right tail. This is a very important point because these tables are set up differently. And it's good to use a table. If you have a table or a table you've got from the internet, that's great. But they're set up differently. Some of them are set up for a single tail test, and some of the tables are for two-tail tests. Now this says right tail probability, which would make me think this is a one-tailed test, okay? But if you look below that, in the next header column there, where you've got T.100, T.050, T.025. So this number, the subscript for the T in that header, so T point sub 0.025, that 0.025 is telling you that's the probability in the right-hand tail, okay? So it's 0.025. So actually, this table is really, it's for a two-tailed test, because the reason being, when you test at 95% confidence, okay, on a two-tailed test, that means there is 2.5% chance you're going to be way out in the right-hand tail, but also 2.5% chance you may be way out in the left-hand tail. So the fact that this says T.025 is very important. If this was the same, if it said 95% confidence, and if it said right tail probability, just like it does, but then this said T.050, that would be a single tail test, okay? But because it says T.025, you know, this is actually doing the two-tail test, okay? There's a 5% chance you're not between this negative T-star and positive T-star value, okay?
Mr. Shelton?
Yes.
I actually have to go. I just wanted to check on the final study guide. It is not on the on Stat Lab. Is it? Are we still should do that, or do we not have to do that?
Did you say it is on there or it is not on there?
It is not on there anymore.
Okay.
I just wanted to make sure that it was. I'm just maybe seeing if I was just missing it or not.
Oh no. Okay. So here's what the situation is. Don't worry about that in Stat Lab. Okay, it's not an assignment in Stat Lab. It won't be. Okay, I think there was one there on one of these classes, and I deactivated it. What I'm going to do, either this evening or tomorrow, depending on when I can get to it, I will post a study guide on Blackboard, and in your email, you'll see it. And I'll just say, hey, here's the things you should look at if you want to review for the final. It's not an assignment. It's not a homework assignment that you're going to get credit for. It's just telling you, here's what the final is going to cover. If you want to study, you might want to refresh on these items, okay? But it won't be a graded assignment in Stat Lab.
Okay, thank you.
You're welcome, and have a great day, Livia. Okay, Levi, I'm going to continue here. Do you have any questions so far? If you can, I don't know if you have a mic. And I got to go to a different screen to see chats. Let me get out of this screen for a second. Maybe I can come back to it and see if you're saying anything in the chat. Okay, no, you do not. Okay, all right, I'll continue. If I can get back to the, that was this one. Hopefully it'll pop back up. Good. All right, that's nice. That cooperated. Okay. All right, so back to this T table. Says right tail probability, but it's also showing you that where it says T.025, so that would be if you're doing a two-tailed test, which when we do a confidence interval, that's essentially a two-tailed operation, okay? So you want the T value for T at 0.025. So on this table, our degrees of freedom is 6 for our problem. We come across to our 95% confidence level, which is on here T of 0.025. So that's correct. It's a two-tailed T value. and the intersection of that row and column is 2.447. So that's our value for T star. Okay, if we're making a 95% confidence interval, that's the value we use for T star. So we're going to say that the true population mean is within plus or minus a T value of 2.447 from our X bar value. Okay. All right. So let me go back to the problem. I've written that down if it'll let me get into the problem. Okay, and here it wants the interval, okay, in this part A. So we could use that T value, and so the formula, again, for the confidence interval is X bar plus or minus T star, which we just determined, times the standard error. So we could calculate that confidence interval just with a calculator. Right, we've already got X bar, they gave us that. So the standard error is just S over the square root of N, which would be 18.8 divided by the square root of 7. That's the standard error. So we can calculate and I'll do it that way this time. I'll just plug it into the calculator. Let me see if I can, you can, I don't know if you can see this screen too also maybe and see that at the same time. Can you see that okay? I'll go into my chat to see your answer. I have to unshare to see the chat, I think. Yeah. Stop share and chat. Can you see this when I had it the other way? So I had another screen up here. What I'm asking is, can you see the problem and this notebook paper at the same time? Is this notebook paper big enough to where you can read it when the problem's being displayed? I can make it out on mine, but I don't know if what you see exactly on your screen, Levi. Let me pull the problem back up again here. And it was here. And unmute. Maybe, well. So can you see the problem and this notebook paper at the same time, Levi? If you answer that in your chat screen, I'll go back and read the chat screen. Then I'll know if I have to keep trying to switch back and forth or not, or if I can just leave it on there. I have the option to see your shared screen or oh, okay. Thank you very much. That's helpful. All right, so I go back to here and here. Okay, so you can switch back and forth. That's very helpful. All right. So what we're doing is we're hand calculating a confidence interval. And again, you could do this in Statcrunch, but if you got a calculator, it's pretty easy to do too, right? So we got 72.2 plus or minus. We looked up T star from that table, was 2.447 times the standard error. And so the standard error was 18.8 divided by the square root of 7. So this gives us our confidence interval, okay? And this was at 95%. 95% confidence, okay? And let's see. So, and just so you recognize it here, so this is X bar plus or minus the margin of error, right? Margin of error. That's what we're doing. So this margin of error is T star times the standard error. That's the margin of error. Okay, which is this part. But now I'm just going to punch this in the calculator. Okay, so 18.8 divided by square root of 7 equals times, yeah, 2.447 equals, so I get 72.2 plus or minus 17.3877. Okay. So that gives me 54.8123 as my lower limit, and $89.5877 as upper limit. Okay, so back to the problem here. We're 95% confident that the population mean is between, that's correct. That's the correct wording. We're confident, it's not a probability thing, and we're confident that the population mean is in this interval, and here's the interval, so we just put it in here. And it wants it to nearest tenth, so 54.8, and upper limit 89.59, 89.59. It doesn't like that. So why doesn't it like that? This is what I did, T star times S over square root of N. That's what I did here. We're at the 95% level. And we looked up T was, did I not put that in there right? Let's see. 54.8. That looks right. Oh, I see. I don't know why I did that. I entered 2 decimals there instead of 1 decimal. So that's what's going on there, I believe. Let's try it again. Yeah. Okay, so that was just, I got a little slap happy there. It wanted 1 decimal place and I entered 2. And so I need to slow down and put those in slower. All right. So part B, let me see if I can minimize, got some things kind of in the way here of reading the whole. There we go. Find a 90% confidence interval. Okay, so what we can do here, the only thing that changes here is we went from a 95% to a 90%, right? That's the only thing that changed in this problem. So all we need really is a different T star value. Now we still got the same degrees of freedom, we've just changed the confidence level. So we can go back to the table and let me see if I don't know if you, hopefully you can see that table. I just pulled the table up again. We're still at the same degrees of freedom, and we're at a 90% confidence interval. And notice what's associated with it. So this number down here is, it's called alpha over 2, okay? Because alpha is 1 minus your confidence. Our confidence is 0.90, so alpha would be 0.10. All right, so if we were doing a one-tailed test, this would say T of 0.10, but we're doing a two-tailed test. Because it's two-tailed, we have to split that probability and have half of it in each tail, right? So we've got at 90% confidence, there's a 10% chance that we're not between the critical T's, basically, right? And so we got a 10% total chance that we're not between them, okay? But we could be either way above or way below. So that 10% gets split, that curve's symmetrical, so half of that 10% ends up being in the right tail, and the other half of the 10% is in the left tail. So this T value here is showing you what's in one of the tails. So that's correct. Anyway, if you just look up 90% confidence here in this table, you're good. And you come down to our degrees of freedom. So our new T value is 1.943. And so we just plug this different T star into our equation here. See, at 95% confident, our T star was 2.447. Now we're 90% confident, and we get a different T star. We get 1.943, and notice nothing else changes, right? We just change that one number and recalculate this, and we're done. So let me calculate that. So 1.943 times 18.8 divided by the square root of 7 equals, okay, plus 72.2. So my new number's 86 point, and it only wanted one decimal place in the answer, so I'm just going to round this to 1. It'd be 86.0. That's my upper limit. And let me calculate the lower limit. So I've got 13.8064. That's my margin of error. That's this T star times the standard error, okay, is 13.8064. That's the margin of error. And I subtract that from 72.2, and I get 58.4 to one digit. Okay, so 90% confidence. And here we had 95% confidence, okay? So if we go back to the problem here, we're 90% confident that the population mean is between, and I just put the interval in here, 58.4, and 86.0. It like that, okay. Now notice, I don't know if I can scroll here. Maybe it'll let me scroll. Yeah. So at notice on this screen at 90% confidence level, see how wide our interval is? It's from 58 to 86. Let's look back up here, see if I can get them both on the screen at the same time. Yeah. So 95% confident, look at the interval. So what's happened here? The interval gets narrower the lower your confidence is. So that seems backwards, you know, to the way we would start out thinking about this. You'd think, Well, if I'm 95% confident, I'm more accurate than I am if I'm 90% confident. But that's not the right way to think about this. The way to think about this is, if I tell you I'm 95% confident in something, it means there's a 5% chance that I'm wrong, okay? So here's how wide the interval has to be if there's only a 5% chance that I'm wrong. But if I can tell you, oh, but a different one where there's a 10% chance I'm wrong, I can actually give you a narrower interval. I can tighten that interval, but the chances that I'm wrong are higher. Okay, so that's why that is. And they ask you that, and they may ask in this one that something about what happens to the interval when your confidence level changes. So at lower confidence, you actually get a narrower interval, which you would think you would want, right? If you're estimating something for someone, you would want to give them a narrow interval. You would want to narrow it down to something which is in line with thinking, well, that's more accurate, right? That's a tighter interval. That's true. But your chances of being incorrect are higher when you give it statistically, when you give it its narrower interval. So that's what's going on there. That's a good place to see that. So let's scroll down. Oh, and here's the question. Which interval is wider and why? So we just explained that. So the 95% interval is wider. So we got two that say that. It has a greater confidence level, okay? And so we use this says, so we use a smaller t, which creates a wider interval, or it's t star. And this one says, so we use a bigger value of t star, which creates a wider interval. Well, look over here. Hey, I don't know if you can see that. That's nice. I can take the cursor and point over there. That's handy. But look up here. Let's see. It's pretty small for me. I can't see that screen very well. I guess, oh, it's backwards also for me, so it's hard to read. But here's the equation for a confidence interval, right? X bar plus or minus, and then this whole thing over here is called the margin of error. So we got T star times the standard error, right? So you can see this plus or minus, this part's going to get bigger when T star gets bigger, right? Or the standard of error is bigger, either one. But if you got the same size standard error, if I have two different values, one with a big T star and one with a small, the bigger T star value is going to make this margin of error bigger. Okay, so as T star increases, as you get a higher number for T star, your margin of error is going to increase. Your interval is going to be wider. So it's going to be wider because, and so we use a bigger value of T star. So that would be true for B, 95. Check answer. It likes it. Next. Okay. State whether each of the following changes would make a confidence interval wider or narrower. Assume nothing else changes. Okay, so changing from a 90%, whether each would make it wider. Okay, A, how would changing from a 90 to a 99% confidence level affect the width of the interval? Okay, so here we're going from where we have a 10% chance of being wrong to only having a 1% chance that we're incorrect, right? So if we have if we give somebody an estimate, but there's just a 1% chance that our estimate does not contain it, that means that interval has to be much wider for that to be true, right? That it covers a lot bigger range. If there's only a 1% chance that we're wrong, then the plus or minus we have to give somebody is much bigger if there's only a 1% chance we're wrong. Okay, hopefully that makes sense to you. So it says, changing from a 90 to a 99% will give us a wider interval, right? Okay, final check. Okay, next question. Let's see, I gotta move this to click something else here. There we go. It says I've not completed the question. Well, I want to complete the question. It's not letting me scroll here. Oh, continue. Okay. There we go. How would changing from a sample size of 300, or wait a minute, yeah. How will changing from a sample size of 300 to a sample size of 10 affect the width of the confidence interval? So let's think about this. Let's go over here. Let me draw it a little bit bigger over here, okay? So confidence interval, and we said it's X bar plus or minus, and here we're using a t statistic, but this works for z's also, right? It's the same thing, whichever statistic you're using, which depends on what sample size you had on, but I'm just using t as an example. But X bar plus or minus T star times the standard error, right? And this would be the standard error of the sampling distribution of the X bars, okay? And they're asking us, it says what happens when you change the sample size from 300 to 10? So n was at 300, and then we go to n equals 10. So what happens to the interval, okay? Well, let's look at our equation. You can see here. So where does n come into play in this equation? N only comes into play in one place, and that's here, okay? Because the standard error is S over square root of n, okay? So let's look at this standard error. Let's say that S is some value. It doesn't matter what the value is. It could be any number, but it's constant. It's the same number. But just for the sake of argument, let's say S is 10, okay? All right. If n is 300, well, let's do it here. Let's use we'll use the actual numbers. How about that? So S was 18.8, okay, over the square root of 300 versus, because we're talking about if we change n from 300 to n equals 10, what happens? So we've got this versus 18.8 over the square root of 10. Okay, now actually I don't need to calculate this. You should be able to see this. So do you think the square root of 300 is bigger than the square root of 10? I'm sure it is, right? Let's see what it is. So square root 300. Okay, so the square root of 300 is approximately 17.3. Square root of 10 is approximately what? 3.16. Okay. Well, here's the point. When n changes, if n gets smaller, which it did here, n went from 300 to 200. If n gets smaller, the square root of n gets smaller, okay? So n smaller gives us square root of n is smaller, okay? That's what happens. So looking back at this equation now, what happens if this square root of n, what happens if this number gets smaller? What happens to this whole thing? If the square root of n gets smaller, this whole ratio is actually going to get bigger, right? Because it's S divided by a smaller number. So that makes a bigger number. So as n gets smaller, as n gets smaller, standard error gets bigger, right? That's what's happening. So that's the effect of n of your sample size on this statistic. If your sample size gets bigger, okay, is n bigger, standard error gets smaller. They're opposite, right? Because n is in the denominator of this term, of this standard error term. So if n is bigger, then standard error is smaller. If n gets small and s stays the same, standard error gets big. And the width of your interval is a function of how big t star is and how big the standard error is. So as a standard error gets bigger, margin of error gets bigger. And the opposite is true, right? Standard error gets smaller, the margin of error is going to get smaller, because this whole thing, remember, t star times standard error equals the margin of error. And your margin of error is how wide your interval is, right? Because you're plus or minus, because your x bar plus or minus your margin of error. So that's what the confidence interval is x bar plus or minus margin of error. So if the margin of error gets bigger, your confidence interval is wider. So now let's answer the question. We thoroughly understand that. Won't let me scroll. Okay. How will changing from a sample size of 300 to a sample size of 10 affect the width of the confidence interval? So the square root of n got smaller, much smaller, which makes the standard error get much bigger because the square root of n is in the denominator. So the standard error is bigger. That means the width of our confidence interval is bigger or wider. Okay, so it's A. Final check. It likes that. And see if I can scroll. I hit continue. Okay. How would changing from a standard deviation of 30 pounds to a standard deviation of 20 pounds, I got stuff in the way here on this screen. I can't, it's covering up what I'm trying to read. And dock to top, where does that go? That's better. Okay. How would changing from a standard deviation of 30 pounds to a standard deviation of 20 pounds affect the width of the confidence interval? Okay, well, let's go back once again. Where does S come into play in this equation? And it doesn't matter if this is T or Z, right? In general, because we could be doing a Z test on something, and it's the same thing, T or Z. It's the X bar plus or minus this statistic, whatever it happens to be, whether it's a T or Z distribution, times the standard error of the X bars, right? So where does the standard deviation come into play in this equation? It comes into play here. S, the sample standard deviation, is used to calculate the standard error, okay? And this one is more straightforward. The other one was opposite, right? When n got bigger, this thing got smaller. But here now, if s gets bigger, this fraction gets bigger, right? Because it's in the numerator. So as a sample standard deviation grows or gets larger, the standard error gets larger. Sample standard deviation gets less, standard error gets less. The width of this interval is proportional to the size of t star and the size of the standard error. So if I make either one of these bigger, this width is wider on our confidence interval. And as S gets bigger, standard error gets bigger, width of the interval gets bigger. S smaller, standard error smaller, width of the interval smaller. Okay, so we've changed from a standard deviation of 30 to 20, so S got smaller, standard error gets smaller, width of the interval gets smaller, so the interval becomes narrower. Okay, how would the weight, well, let's see, the weights of 4 randomly independently selected bags of potatoes, okay, are 20.7, 21.2, 20.9, and 21.2 again. All right. And it wants us to calculate an interval. It said find a 95% confidence interval for the mean weight here. Okay, we've done this several times now. This is the same kind of problem, right? You could either do, let me think here for a second. You could calculate S from this sample. You could get the standard deviation from using just these numbers, and you know that n is 4, so you could calculate your standard error from these numbers, right? And it's telling us it wants a 95% confidence interval. So we have to say, well, which statistic are we using, T or Z? Well, we look at our sample size and it's small. It's n equals 4, which is less than 25. So we know we're using T. So we have a T star, and we know the degrees of freedom is going to be 3. It's going to be n minus 1. So we can calculate or look up T star. We can calculate or look up the standard error, and then our confidence interval is just the X bar, which we would calculate from this sample, plus or minus T star times the standard error. Just the same thing we've been doing, okay? We've done that many times. So you do that for this data, and I'll just show you one more time in Statcrunch how you can get the confidence interval quickly in Statcrunch. So hopefully I'll be able to share this without too much difficulty. So if I say stop, share, problem is it makes me leave. Let me go here and select it first, see if it'll let me do that. See if it'll let me put this into, I'm gonna click the icon, see if it'll let me put that in Statcrunch, and then maybe I can stop share and reshare. Let's try it now. Stop share, reshare, and here. That is our data, okay? So we can get the 95% confidence interval very quickly if you just say stat, and this is t-stats, small sample size, one sample, we had the data, and we just we select the data, that moves it over here, then we just tell it, yes, the confidence interval, okay? And compute. And there we have it. So it's 20.6102, 21.3898. 3898. There's the confidence interval. Gives us our standard error, our X bar, and our degrees of freedom also there. Okay, so let me go click on this and stop share, reshare, reshare. Good. Okay. And those are the numbers I got. 20.6, it wants 2 decimal places. Those are the numbers we got just now, okay? Does this interval capture 20 pounds? So just say, is 20 pounds inside this interval? And no, it's not. 20.0 is less than 20.6. So it's not in the interval, okay? So there is enough evidence to reject the mean of 20. That much is clear, okay? And then it says it's not plausible the population mean is 20. Well, that's correct. What's this other one say? It's not plausible the population mean is, oh, this one says the interval. Wait a minute. All right, back up here. Does the interval capture 20 pounds? No, it does not. So we know we're going to reject, okay? So there is enough evidence to reject, okay? But this one said the interval captures 20 and it doesn't. So I was, of the two that say there's enough evidence to reject, we got to go with this one because this one says the interval does not capture it. So this is all consistent. The interval does not capture it, which means there is enough evidence to reject that that is the mean, okay? So it's not plausible that the population mean weight is 20. It's just what it says it is. That one is, and that's the way that this should be worded, because it's not in the interval. There is enough evidence to reject it. It's not in the interval, you're going to reject it. Okay, which means if you're rejecting it, that it's not plausible that that's what it is, because you're rejecting that. Okay. Next question. The weights of 4 randomly, independently selected bags of tomatoes were, this is the same kind of problem, okay? Let's just get this quickly from Statcrunch. So I think I can go here. It wants a 95% confidence interval. Or wait a minute, you don't click that one, you click this one to get the data. Open in Statcrunch. Okay, now stop share, reshare. Select it again, reshare it again. There, now we're getting somewhere. Stat, T-stats, one sample with data. Select the variable. We want a confidence interval. We compute. Okay, and we get 4.9363, and for the lower limit, 5.4137 for the upper limit. And again, on all of these, when you're doing calculations, always look out to 5 decimal places, round to 4. And then you can use that number in another calculation step. But all your numbers, look to 5, round to 4. Then when you're finished, slow down, because I make mistakes all the time. I give it more decimals than it wants, and it says it's wrong, and actually it's the right answer. But in your processing, always look to 5, round to 4, use that in the next calculation step, etc., until you're finished calculating. When you're finished, look at 5, round to 4, then look and see what it wants. Then if it says round to 3, take the 4 numbers you've got and round to 3. But if you round too early in the process, you can be off a digit. You can be off in your last decimal place, okay? All right, so let's go back here and select this. And then we say stop share. I think one thing, you've got to select things before you stop the share. Now, see, that time it did something different again. I don't know why it did that. I want to reshare. Stop share. Share screen. Should be that one. Okay, so we put our interval in here and it wants rounded to the nearest hundredth, okay? So we've got the nearest hundredth would be 4.94. 4.94 and 5.44. 5.44. It doesn't like that. What? Okay. Let me go look. What did I do? Did I not write it? Maybe my writing's a little messy there. That's 4.94, 5.44. Okay. Maybe my writing, I jotted it kind of. Let me go back to Statcrunch here, if I can get back to it. There. Okay. Get out of that. Oh, yeah, okay. That's my typo there. Let me share this with you. Stop share. Reshare. There. There. Okay, so I wrote it down too fast. I looked at this number and haste makes waste. What I wrote down was 4.37. I left this one out. I just looked at it too quick and I rounded here. Anyway, I wrote this number down incorrectly. So it's a typo. I left the one out. It's what I did. So this would be 4, and it wants it to hundredths, I believe. So this would be 5.41. Yeah, and I had entered 5.44. Okay. You'll have that. All right. Let's go back. Select. Okay, so let's put the right number in there, Mr. Shelton, okay? 5.41. Just say no to typos. Check answer, okay. All right. Does the interval capture 5 pounds? So is 5 inside this interval? And so remember on these intervals, I think you know this, but this parentheses here technically means it doesn't include that number. It means it goes up to that number. So that anyway, this is all the numbers between 4.94 and 5.41. And so does the interval capture 5.0? Yes, it does. Okay, so it does capture, rule that out. So this is yes, All right, so let's look at these two. It does capture it. So there's enough evidence to reject it. Well, no, if it's in the interval, you do not reject. That's what the test is. You look to see, is it in the interval? If it is, you do not reject. And since you're not rejecting, it means that it is plausible that the population mean is what the claim value for it was, which here was 5.0. It says bags of tomatoes labeled 5.0. So it's plausible that that is the weight. So that's C. Check answer. Next question. Okay, according to a poll taken, and now we're into proportions, right? Because you can see here it's got a p-hat it's talking about. So we're not doing means testing, we're doing proportions testing now. But this central limit theorem process is very similar. That's part of the beauty of it. It's so widely applicable. All right. But according to a poll taken, adults were asked, are they thriving, struggling, or suffering? Probably a little of all of those, right? Most of us, most of the time, we're doing well in some areas, but we got some grief in others at the same time. Anyway, 243 out of 430, 243 out of 433 said they were struggling. What's the value of p-hat? So p-hat is just a sample proportion, which it says, what's the value of p-hat? The sample proportion that say they're struggling. So we just get the value of this ratio. 243 out of 543 that were polled. So we just take that ratio, 243 divided by 433 equals, and I get 0.5612. There's my 4 digits that I like. And it wants 3 decimal digits. And so we give it 0.561. 0.561. And the next question is check conditions to determine whether you can apply the central limit theorem. Okay. So in proportion testing, there's 3 conditions to be able to use the central limit theorem. And what's it mean when we say we're using the central limit theorem? It means we're allowed to do all these critical statistic calculations that we do with the normal curve or with the t-curve. All of those hypothesis tests and confidence intervals tests that we do, those are all because the central limit theorem is true, okay? But there has to be certain assumptions. Certain things have to be valid in order to be able to legitimately use the central limit theorem. And so for proportions testing, there are 3 things that have to be true to justify us making use of these curves and these tests the way that we do. The 3 conditions, okay, so random and independent condition, okay, can reasonably be assumed to hold. So that says the sampling. When you go get a sample, it has to be a random sample, and the samples have to be independent. And independence means if I go get, I go poll one person, it means the next person I poll, that their answer has nothing to do with what the first person answered, okay? It's completely independent of that. So you can see that sometimes is a difficult requirement to fill, right? Get people that are actually independently thinking and not doing group think kind of thing would be one example. But anyway, independent sampling. So each sample has nothing to do with previous answers. It's purely that person's answer. Or okay, the large sample condition holds, and what the large sample condition in proportion testing is that there's 2 parts to it. Okay, n times p, the sample size times your population parameter, has to be greater than 10, okay? Now, we don't always know what the true population proportion is, but so we use p hat to estimate it when we're checking for this condition. So we look at our p hat and we say, well, let's just use that as an estimate of the true population proportion for the purposes of testing it to see if this condition holds. And so p hat will be, you know, hopefully a ballpark number that's somewhere in the range of the real population. And so you take n times p hat. Is that greater than or equal to 10? If it is, you fulfilled half of that large sample condition. The other half of the condition is that n times the quantity 1 minus p also has to be greater than or equal to 10. And again, if you didn't know p, you can use p hat as a substitute for it. So n times the quantity 1 minus p hat has to be greater than or equal to 10. So those two things constitute the large sample condition. So we're doing conditions to determine whether you can apply central limit theorem. So we have the random and independent condition, we have the large sample condition, has to hold, and then a big population condition also has to hold, all right? And the big population condition says that your population size has to be at least 10 times larger than your sample size. That's what the big population condition is. So population size must be greater than or equal to 10 times your sample size. Okay, those are the three conditions that say it's legitimate to do this. Okay, now it wants a 95% confidence interval, and we can calculate that for proportions. Since we're allowed to, we're going to say those conditions hold for this problem, okay? So let's go into Statcrunch. I'm going to jot down here, we got 243 out of 433, okay? And that's all we have here, okay? And we want a 95% confidence interval on what we think that would contain the true population proportion, okay? So we'll go into Statcrunch. And we'll share this. Share that. Google Statcrunch, yeah. Okay, so we can go to Stat. And now we're talking about proportions. So we come down here to proportion stats, right? Stat proportions. One sample. That's all we have. And we don't have individual information in that sample. We've got the summary. We just know that 243 out of 433 indicated they were suffering, okay? So that's summary information. So here we enter the number of successes. So a proportions test can be applied to anything that has a dichotomous value, that is a two-valued variable. It could be true or false, yes or no. And here we're testing just to see if people are suffering or not suffering. So a success is the affirmative, somebody that is suffering, okay? So 243 successes, 243 people suffering out of 433 people polled. Now, it said it wanted a confidence interval. So we can just, I believe we could just check confidence interval, okay, and say compute. And we get 0.5145 and 0.6079. there's different ways that you could do this as well. Now, let me show you here. I think you can still see this. So it's the same. Okay, there's a couple things to note when you're dealing with proportions, Levi, and class. For one thing, you no longer have to make this determination about are you going to use T or are you going to use Z. You don't have to worry about that anymore. When you're doing proportions testing, it's always a Z test, okay? So we know our test statistic is going to be a Z distribution, and there's just one Z distribution. So degrees of freedom is not going to play a role. So you don't have to worry about that. But our formula is the same. It looks very much the same, except instead of, so a confidence interval for proportions, instead of, okay, we've been talking about means testing, right? And confidence intervals around means. Now we're doing confidence intervals around proportions. So instead of X bar plus or minus margin of error, and what was X bar? X bar was the sample mean, right? Well, what would it be for proportions? It would be the sample proportion. So that's P hat. So it's going to be P hat plus or minus your margin of error. It's the same general form of the equation. It's just we're dealing with proportions and not means now. So this is still looks very similar to what we were already doing. It's just we know with proportions, we only use the Z statistic. So this is going to be a Z star value, and this is going to be times our standard error. So it looks very much like the means testing, right? Just small differences. This is not X bar anymore. It's P hat, which is our sample proportion. And this standard error is the standard error of the sampling distributions of P hat. And it has its own formula, right? Standard error equals the square root of P times 1 minus P over N. And what we were talking about earlier applies here. Sometimes we don't know the true population proportion. That's what this P is. When we do not know this, it's okay for us to use P hat. It works pretty well as an estimate for what this is. So we're trying to calculate the standard error of P hat. We can estimate the population proportion. We could put P hat in here if we don't know what P actually is, okay? And that would give us our standard error. So that's what's going on there with confidence intervals for proportion testing, okay? So let's go back to the problem, which is there. See, I don't know why it does that. Why it doesn't go back. I'm not sure. Is that question 9 that we were on? Now, I don't know why it's doing this. No, we were past there. Okay, here's the problem. Let me reshare this. I don't know why that comes up there. Okay, well, I don't think it's showing you that. It doesn't have it outlined, so I don't think you're seeing that. Let me try again here. Share screen. Maybe, oh, that's what it is. I think you got to double click it maybe and then share. Let's try that. There, okay, you can see that. Okay, so we just calculated the 95% confidence interval by going into Statcrunch, and we could have done it. We could do that a couple different ways. We did it the fast way, where you just go in under proportion stats, right, and select confidence interval. So, and the numbers we got for that, and it wants 3 decimal places, so that'd be 0.5155, and the next number would be 0.608, 0.608. Okay. Oh, we're into another problem. Okay, it's another proportion problem. And it says, poll asks certain country whether immigration is a good thing or bad thing. That sounds familiar. You hear a lot of that these days. People have strong opinions about that. Out of 1,075 respondents, so that's our sample size, that's N, is 1,075. 542 said immigration is good. Okay, so that will be considered successes, right? In the language of proportions, we have successes and failures. And so we're going to call somebody that thinks immigration is good a success. All right, here. So what percentage of those taking the poll said immigration is a good thing? So that's the same thing as saying what is the value of p hat, okay? P hat is that percentage. Well, p hat is the proportion, so it'll be a decimal number, right? And then multiply times 100, that's the percentage. So 542 divided by 1,075 equals, so the decimal number, p hat, is 0.5042. So p hat equals 0.5042, but it wants to know what percent of people. So that would be, and it wants round to 1 decimal place. So 0.5042 would be 50.4%. I thought I was typing that in there. 50.4. Okay, that's p hat, essentially. That's the percentage that think immigration's good. Check the conditions to see if central limit theorem hold. Okay, so the random and independent condition needs to hold, so it can reasonably be assumed to hold. So it says a poll asked adults in a country. I guess we'll assume, well, this is the condition for it to hold, that random and independent sampling. And here, it doesn't really tell you that here, but I think it's really just wanting you to say what the conditions are here, right? If you were doing a test, I mean, if you're doing this actual statistics, this is an actual study, you'd have to ensure that these were random and independent samples, okay? The large sample condition, so we can check that here, right? So we use, we don't know what p is, but we know what p hat is. So we'll take n times p hat, and n is our sample size. So that's 1,075 times p hat, which is 0.5. So that's going to be a number, you know, in the hundreds, right? You're taking a little more, tiny bit more than half of 1,075. So that's going to be a number a little bit bigger than, you know, 500 and something. You know, anyway, the point is that number is much bigger than 10. That's all it has to meet, right? So the large sample condition does hold because 1,075 times 0.5042 is a number much bigger than 10, so that holds. And then also the second part of that condition is n times 1 minus p has to be greater than or equal to 10, okay? So n times, and we'll use p hat to estimate p with. So n times 1 minus 0.5042. Okay, well, that's still almost 0.5, right? It's 1 minus 0.5042 is 1 minus 0.5042 is 0.496. And if you round that off, it's still, that's another number that's around 0.5. So a number very close to 0.5 times 1,000 is going to be 500 and something. So that's way more than 10. So that large sample condition does hold, right? Okay. So over here, this is large sample condition. You got NP greater than or equal to 10. And you got n times 1 minus p greater than or equal to 10. And again, this is p here, but if you don't know p, you can use p hat to estimate it with. N times 1 minus p, and we use p hat to estimate p, and that has to be greater than or equal to 10, right? And this number ended up being 1,075 times 0.4958 equals times 1075. So that number's about 5 approximately. I'm rounding it. 533 people, right? Much greater than 10. Big population condition, does that hold? Well, this is a poll asked adults in a certain country. So the big population is talking about here is the population of a country. Is that at least 10 times bigger than our sample size than 1,075? Well, yeah, probably, right? A country is going to be a lot of people. That's going to be substantially larger than 1,075. So we can say that holds. Check answer. Good thing. Okay, 95% confidence interval is. So we can calculate that. We'll use the Statcrunch to do that with. So let's see. We're going to Statcrunch this way. Statcrunch. I got to share this. Stop share. I think I figured out you have to double click things and then you can reshare. If you single click them, they don't always share right. Okay. So we're wanting a 95% confidence interval on this, and we had, it's a proportion stat, one sample. We don't have data, we just have summary, right? We just have a number of successes out of a number of attempts, if you will, or which is your sample size. So number of successes we said was 542, and the sample size was 1,075, and then we're going to get a confidence interval, and we say compute, and it gives us 0.4743 and 0.5341. And again, we're doing it this way. The other way you could have done this is you could do it with a calculator. Just take p hat, and p hat, that's number of successes out of the total, right? And that's well, okay. So that's what p hat is. So it's p hat plus or minus z star times the standard error. So this is how you would, calculate the confidence interval. So you would look up z star for 95% confidence, and for 95% confidence, z star is 1.96. We already know that. If you're at if this is if 95% confidence, okay? If you have a different confidence level, Z star is a different value, and you have to either look it up in a table or use technology to see what its value is. And I can show you, let me show you how to do that, just to refresh your memory, okay? If you're watching this getting ready for the final, it doesn't hurt to see it again. So let's go into, we're already in Statcrunch, good. Let's go Stat, Calculators, Normal. What we're going to do here is show you how to get the value for Z star, okay? How to get a value for Z star. And when we're talking about confidence intervals, we're talking about an upper limit and a lower limit. So we want to select between, right? And remember, if we set mean equal to 0 here, standard deviation equal to 1, this thing is now z-scores. That's what this is. This is the standard normal curve, and these are z-scores. So this down here really is z. The probability that z is between two numbers is such and such. So if we want a 95% confidence interval, we can just put 95 in here, 0.95, say calculate. This gives us z star. So our z star is 1.96, and that never changes. So anytime we're doing a 95% confidence interval and you want to know what z star is, it's always 1.96, right? So back over here, that takes care of z star. And let's write down, I like doing this just to keep it fresh in people's minds. Let's look at what some of the other values would be. If we were doing a 99% confidence interval, so for 99% confidence, I put confidence up here, okay? Make a little table. And then I put Z star. Z star is 2.5758, 2.5758. And that number never changes. If you're doing a 99% confidence level, that's always what the number Z star is going to be, okay? Let's look at, and we did 95 already. We see it's our old friend 1.96. So 95% is 1.96. Okay, and then let's do 90%. That one's, occasionally people want to know that. 90% confidence, what's Z star? 1.6449. Okay, so there's your three Z star numbers for your most common levels of confidence testing. And you do that, if you remember these, you never have to calculate them or look them up in a table again. This one you use all the time. So anytime you're dealing with a two-tailed test or a confidence interval, you know that Z, the critical, this is called the critical value, Z star, is 1.96. But there it is for 90, 1.664, and for 99, 2.5758, okay? Back to calculating our confidence interval here. So we've got Z star, and we've got p hat. So then standard error, we said before, standard error, for which is really the standard deviation of the sampling distribution of p hat, but it's called a standard error, is equal to the square root of p times 1 minus p over n. And if you don't know the population proportion p, you can substitute p hat here. You can write p hat, okay? That's how you calculate it. But so I'm not going to go through that again. We calculated it this fast way, just letting the computer do it. And have I written those numbers down so I can transfer them to something else? I don't know if I did. Let me see. I'm going to write them down. 0.4743 is the lower limit. 0.5341, 0.5341, that's the upper limit. Okay, let's go back into problem. Hopefully, no, it didn't go there that time. Are we in this one? Was this our problem? 10, or no, I think maybe we were in 11. Maybe that was the problem. Yeah, we were in 11. Okay, now I should be able to share this. Share, stop share. Okay, there we are. So we're right down. It wants 3 decimal places. So we had written down 4, so 0.474, 474, and here we have 0.5341. Ah, there I go again. It asked for 3 and I put 4 in. Can't help myself. All right. Okay, new problem. Simple random sample, 1,400 young people. Let's see. All right. So n equals 1,400, and it said 88% had earned a high school diploma. A high school diploma, 88%. Okay. So what's that proportion? A proportion would be 0.88, right? A proportion is always a number between 0 and 1. And you multiply 100 times a proportion, you get a percentage. And so you divide a percentage by 100, that gives you the proportion. So this is actually it's p hat, because this is a sample. In this sample, the proportion, so that's p hat equals 0.88. What's the standard error? Well, we can do that real quick. We're going to use, we don't know p, so we're going to use p hat as a substitute for p in the equation, which standard error equals square root of p times 1 minus p over n. We don't know p, so we use p hat as a substitute for p, because we don't, if you knew p, you would use the actual p here, but we don't. So we say square root of p hat times 1 minus p hat over n. And actually in statistics, it gets, this is a pretty good approximation, but there you can be a little more accurate than this, but then you're getting into a lot more technical material than we're going to do in this class. This is a good approximation here, good enough for us. Okay, so we just plug these numbers in. So we have this. So the standard error. Remember, this is what standard error is. It's the standard deviation of this sampling distribution. It's the standard deviation of the p hats. If we went and sampled and got a p hat, and then we went and did that again and got another p hat, and then got another p hat, well, they're going to vary some, right? Each one of those is going to vary. And we get many, many of them. Well, they'll have a certain variation, and there's a standard deviation associated with that, right? And the standard error is that it's the size of one standard deviation of p hat. So when we do all this business with the curves, right, we have z-scores. These z-scores are really a count of standard errors, okay? That's what you're doing. You're saying, how many standard errors am I away from this center point? But back to the problem here. So let's just plug the numbers in. We got square root of 0.88 times 1 minus 0.88, so that would be 0.12 divided by n. N is 1400. So that's our standard error. Standard error equals this, which equals, so let's do it here. 0.88 times 0.12 equals, divided by 1400 equals, let's take the, okay, that's a very small number. It's 0.0000754, that's enough. Okay, so I want the square root of that. So square root of 0.0000754, and I get 0.0087 to 4 decimal. That's the standard error. Okay, and it says round to 4, so let's try that. 0.0087. It likes it. Good. That's progress. Find the margin of error. Okay, margin of error. New paper. Let's move that stuff. All right, margin of error. So we have confidence interval equals p hat plus minus z star times standard error. Okay, and this part is the margin of error. Okay, confidence interval is p hat plus or minus the margin of error. So this stuff is the margin of error. And we were testing at 95% confidence, so we know z star is 1.96. And our standard error we just put in there, which is 0.0087. So this is our margin of error. So that times 1.96 equals, so margin of error equals 0.0170 to 4 decimal places, right? 0170, yeah. Okay, round to 1 decimal place. To 1 decimal place, it would be 0. I didn't like that. So what's up here? Okay, it says use 1.96 for z star. We did that. Okay, so where am I off? Find the margin of error using a 95% confidence interval for estimating. Okay, plus z hat. Oh, I see what the problem is here, I believe. It says round to 1 decimal place. Well, 0 is not 1 decimal place. 0.0 is 1 decimal place. That should be it. That doesn't like that either. Okay. Some days it's diamonds, some days it's stones. We'll get through this though. So what's going? Well, it liked our standard error here. Okay, that's what I'm using. 0.0087. Find the margin of error using a 95% confidence round to 1 decimal place. Okay, I'm a little bit stumped here. It should be 1.96 times 0.0087, and that's what we did. 0.96 times 0.0087, and I get I see what the problem is. This is not smart enough instructor problem here. Okay, and I'm glad I made the mistake. Hopefully this will help you so you won't make this same mistake. Here's the problem here. They want the answer in percentage. And I've calculated the answer as a proportion, okay? So the proportion for this margin of error is 0.017, and they want a percentage answer. So that would be 1.7%, okay? 1.7. So if you can see over here, here's a margin of error, which is correct, but this is a proportion, okay? I didn't write that. A proportion. They want Stat Lab wants a percentage, so 0.017 times 100 equals 1.7. Check. Okay, there we are. All right, slow down and read. Report to 95% confidence level. And notice they want percentages again. Okay, so we had, let me get to 4 digits. It's 0170. This is 0.0170. Okay, so it wants the 95% confidence level. We know 0.0170 is the margin of error, so we just take p hat, which was what for this problem? Did I write that down somewhere? Yeah, p hat was 0.88. So the confidence interval is p hat plus or minus the margin of error, okay? So it's 0.88 plus or minus 0.017. And this is at 95% confidence because we used a z-star of 1.96. So this is our confidence interval, okay? So 0.88 minus 0.017 equals 0.863. 0.863, that's our lower limit, and 0.88 plus 0.017 equals 0.897. 0.897. So there's our confidence interval. Now it says round to 1 decimal place, and it wants percentages. Okay, 86.3 to 89.7. Okay, it likes that. Suppose that in the past, 80% of all young people earned high school diplomas. Does the confidence interval that we calculated in the prior work support or refute the claim that the percentage of young people who earned high school diplomas has increased? Okay. So here we would have write down our intervals. 86 confidence interval. 95% equals 86.3 to 89.7. And these are percents, right? That's our confidence interval. And it says, suppose, okay, in the past, 80% had diplomas. All right. It says, does our confidence interval support the claim that the number has increased? Okay. So if the number has increased, if you think of this in terms of hypothesis testing, you would say that the null hypothesis, which we're not doing a hypothesis test per se here, but thinking of it in those terms would be that P equals 80, okay, would be what you'd be testing if this is what it was known to be in the past. So when you go get a sample, you're testing to see if this is actually the case anymore, right? But there's different alternatives you could have. You could have that it's just not equal to that. That's one alternative. Okay, another test you could do, you could test that it's actually greater than that. And then the last test you could do, you could, as your alternative, it could be, you could test, is P actually less than that? Well, in this problem, there's a claim that it has increased, okay? So HA is that P is greater than 80%. That's the alternative, okay? So this would be the hypothesis you're testing if we were doing a hypothesis test. But let's look at what we've got. Here's our confidence interval based on our sample, 86.3 to 89.7% at 95% confidence. Okay, so does that support the claim or refute the claim that it has increased? Well, it supports the claim, right? Because 80% is not in our interval. 80% is much lower than what our interval indicates. So our interval would support the claim that it's increased. So they're not really thinking of it in terms of a hypothesis test per se here. They're just saying this general claim that it's increased, does our interval support that or refute that? And our interval would support it. Yeah, we've got higher numbers than that in our interval. So our interval does support the claim. There's two answers that say that. And it says this because 80 is in the interval. Well, it's not. It's because 80% is not in the interval. So there you are, D. Okay, I made that maybe more complicated than it had to be. You don't have to think about hypothesis testing for that. They're just saying, are you supporting or refuting this claim? So you just look at your interval and the value that it was in the past and see where that fits in there. Okay. Next question. Simple random sample of 800 people aged 20 and over in a certain country, proportion with a certain disease was found to be 0.165 or 16.5%. What's the standard error of the estimate of all the people in country aged 20 and over with the disease? So standard error is that square root of the quantity P times 1 minus P divided by N. We've done that a couple times in this video. So let's just write it in here. Square root of P times 1 minus P over N. And we don't know P, but we do know P hat. So we're going to use P hat as a substitute for P. P hat times 1 minus P hat over N. And so what's P hat here? P hat is 1.165, okay? So square root of 0.165 times 1 minus 0.165, all divided by N, which is 800. And we'll plug that into the calculator, 0.165 times parentheses 1 minus 0.165 in parentheses equals divided by 800 equals a small number. So we have the square root. This is the standard error, is the square root of, I got 1.722 e to the minus 4. So that means times 10 to the negative 4th power. That's the same thing as the square root of 0.0001722, okay? This would be 1 times 10 to the minus 4th, 0.0001722. So we take the square root, excuse me, 0.0001722. And we get standard error equals the proportion for it is 0.0131. So that's 13.1%. And it doesn't ask for a percent here. So this is in proportion. It says round to 4 decimal places, 0.0131. Okay, likes that. Find the margin of error using a 95% confidence level. Okay. So again, in proportions, we're using Z for our statistic, and Z star at 95% is always 1.96. So the margin of error equals Z star times the standard error. Well, I can write that out real good. Standard error. This is standard error here, okay, equals 1.96 times 0.0131. Okay, and the margin of error will be in a well, they list it there in the proportion form, but let me get the number. 1.96 times 0.0131 equals, I get 0.0257. 0.0257. They want 3 decimal places. That would be 0.026. 0.026. Okay. And report the 95% confidence interval. Okay, so you just add and subtract the 0.0257 to what you got for the p-hat value, right? Okay. So p-hat plus or minus margin of error. And p-hat was 0.165 plus or minus 0.0257. So 0.165 plus 0.0257 equals 0.1907 is the upper limit, and 0.165 minus 0.0257 equals 0.1393. Okay. Confidence interval 95%. And it wants 3 decimal places. 0.139, 139, upper limit. I said 9, but I hit a 0. 0.139, upper limit. 0.191, 0.191. Okay. According to a government agency nationally, 17.8% of all people in the country age 20 or over have the disease. Okay. Does the confidence interval that we found support or refute that claim? You just look at the interval and look at their numbers. So 17.8%, we have to change that to a proportion, right? So we've got apples and apples because our confidence interval's in proportions up there. So we just divide the 17.8% by 100. That gives us the proportion number. So our proportion is 0.178. That's our proportion, okay? 0.178. And if you look at 0.178, that fits well inside that interval up there, okay? So the confidence interval Okay, what is the claim? It says the claim is that 17.8% have the disease. Does it support or refute the claim? Well, it supports the claim. It's in the interval, so it could be that. It's not definitely that, but it certainly could be that. So it doesn't refute it. It doesn't say, no, it can't be that because you're not in our interval, because it is in the interval. Since the value, oh, and I guess we just type it in here, 0.178, that's the proportion, is contained within the interval for the proportion. Check answer. Okay. A poll, so we're on to a different problem here, okay? New piece of paper. Poll asked for people's opinion on whether closing local newspapers would hurt civic life. 428 out of 1,001 said it would hurt civic life a lot. And I'm going to go out on a limb and say that's maybe older people that think it would hurt, because older people are used to newspapers and not so much cell phones and computers. Okay. Find a proportion who said that it would hurt. So we just convert that to a proportion. We got 428 successes divided by 1,001 in the sample. So p hat's 0.4276. 0.4276. Round to 3 decimal places, it says 0.428, 0.428. Okay. Find a 95% confidence interval. Well, let's just use Statcrunch because that's quick and easy, okay? Assume it's a simple random sample. That's necessary to be able to do it. So let's go into Statcrunch here. And it should be, okay. So here, let's go into proportion stats. So proportion stats, one sample with summary. Well, all we have is the number of successes out of the number of attempts, essentially, or the total. We don't have individual data. We have a summary, and it's just one sample. This is the proportion for our sample. Number of successes, we just enter it, 428. Number of observations, 1,001. Confidence level, okay, that's it. Then we click on confidence interval. It's called a standard walled test, and we get 0.3969 is the lower limit, 0.4582, 0.4582 is the upper limit, okay? So confidence interval. And note it's a 95% confidence interval there. All right, and okay, back to the problem. Oh, I don't know if you see that or not there. I think maybe you weren't seeing it, so let me do it again. Well, you should have. Stop share. There, now you can see it. Okay, so what I did, again, we went stats, proportion stats, one sample with summary. Number of successes, 428. Number of observations, 1,001. And we tell it we want to do a confidence interval, and it says level, 95% confidence. Okay, compute, and we wrote those numbers down to 4 decimal places. Okay, so we go back into the problem, and I don't know why it does that. It doesn't go back to the problem again. That's don't know why. Let's go here. Yeah, that's a wrong thing. Let's close that out. Okay. Here we go. Maybe it'll let us get back in here. There it is. Okay. All right. Don't know why it's doing that. Stop share. It's Google Chrome here. Come on. Let's. Okay, there's the problem. Now, share that. Share. Every time I tell it to share, it goes back to this other screen. There, but I don't know that you can. I don't think you can see that one. Stop share. It's not highlighting it the way it did before. So I don't think you can see that. Do you see that, Levi? Right now on your screen, 7.4.60. Do you see that problem if you're still watching? I don't know if you're still there or not. I know this is a long process here. Okay. I don't know why this, oh, that says Safari. I see what, that shouldn't be. Yeah, it's in the wrong one there. Let's go. But it said Google. That's what's throwing me here. Google Chrome, do homework. Here. That's Google. Share. That's Google. Okay, I got to pull the assignment up again, I guess. I don't know why I did that. Okay, now maybe we can, there. I don't want to leave. Okay, we're back. So I'm going to enter to 3 decimal places, 0.397 for the lower limit, 397, and the upper limit, 0.458, 0.458. Check answer. Okay. Find an 80% confidence interval. Okay, so what changes here is just Z star, right? That's the only thing that changes. We got this equation, P hat plus or minus Z star times the standard error of the sampling distribution of p hat. So Z star just depends on the confidence level, right? Confidence interval equals. So you give me the confidence level you're talking about, and I'll tell you, and that specifies a certain Z star, which specifies where this interval is located. Okay. So it wants an 80% interval. Let's go back. I have to back up here. Well, I'll just do it. Okay, so what was p hat here? P hat, did it tell us? No, that's a different problem. Oh yeah, okay. P hat was 0.4276 plus or minus, and we need to know Z, what is Z star for 80% confidence. Here's how we get Z star, one of the ways, okay? Let's go into Statcrunch. So if we say question help, Statcrunch, we want a Z star for 80%. All right. So I got to share this with you. Stop share. Okay, good. Stat, we want a Z star for 80% confidence. So let's go into calculator. And this is a normal, right? We're going to use the standard normal curve to get a Z score. Or in this case, it's going to be the critical Z for 80% confidence. So normal, since it's a confidence interval, we want between, and here we want 80% confidence. So it's 0.80 probability. So this says mean 0, standard deviation 1. That makes this into a Z-score calculator because we're in the normal curve. We have a mean 0, standard deviation 1. Those are Z-scores, okay? So compute. Here's our critical Z, 1 point. Okay, so Z star right up there is 1.2816 times our standard error, okay? And what was our standard error? I don't have it anymore, so I got to recalculate it. Standard error equals p hat, well, square root of p hat times 1 minus p hat over n. We can get this, we could get the standard error from Statcrunch, okay? Let's go get the standard error from there. Let's go to Statcrunch and proportion stats, one sample with summary. Number of successes was 428. Number of observations was 1,001. Okay, and if we say confidence interval, I think that gives us, let me say compute here. Yeah, we get our standard error when we do that also. So there's a standard error. Standard error here is 0.0156. Okay, so this is 0.0156. So here's our, this is Z star for 80% confidence was 1.2816. And our standard error just has to do with our p hat value. We can calculate standard error just knowing p hat and the sample size gives us our standard error. And this was p hat. So now we have our confidence interval here. Let's go back. I think you could also do it, and so we could plug that in a calculator and get it, but we could also go stat, proportion stats. Let's see. Oh, we can put in a different confidence level here and get that also. So let's do it that way. Number of successes, 4 to 8. Number of observations, 1001. Confidence level, 0.8. Okay, it wanted a 80%. I put too many decimal points in there. It wanted a 80% confidence. A confidence interval for the 80% confidence level. Okay, so that's what we've done here. We've put 0.80 in, and here's our p hat essentially. 428 successes out of 1,001 observations. P hat is that ratio. That'll give us the confidence interval, or we could calculate it out the way we were doing it. Either way, this is quicker, I guess. So lower limit 0.4075, upper limit 0.4476. So I put confidence interval 80% level equals. Let's go enter it. Go enter that information. I gotta reshare this, stop share. Okay, round to 3 decimal places, 0.408, 4082, 0.448, 0.448. Okay, and now you can see here before I go on, because probably the next question is going to have us compare this interval at 80% confidence to the interval we had at 95% confidence. And you see what's happening here? We're getting narrower with a lower confidence, okay? So once again, you can specify a narrower, a tighter bracket, but you have a larger chance of making an error. Here we'd have a 20% chance that we're wrong, that it's not actually in this interval when we specify this interval. Up here we have a wider interval, but there's only a 5% chance that we're wrong. So that's the trade-off you make when you specify a confidence interval or you test at a confidence level. You can give people a tighter bracket on your estimate, but then your confidence is lower when you do that. And that's what it'll ask us about next. So it likes that answer. Continue. Which interval is wider? Okay, the 95% is wider. There's 3 of those that say that. Okay, this interval needs to be, oh, it says to get a higher degree of certainty. Well, that's a really odd way of, okay, which interval is wider? The 95% interval is wider, and then there's 3 answers. This is to get a higher degree of certainty. The interval, this doesn't make a lot of sense the way that's worded, but I think we could rule out B and D because it says widen just on the right side, widen just on the left side. Well, no, the interval is always kind of symmetrical about your p hat value. So yeah, if you want a higher certainty, yes. And when they say certainty, they're talking about confidence level. I guess if you want a higher confidence level, the interval needs to be widened, because that's what's happening here, right? As we go from 80 to 90, our interval gets wider, or I'm sorry, not 80 to 90, but 80 to 95. The interval gets wider. So if we want more certainty than 95, if we want 99% confidence, it would have to be even wider than that, right? So that's just weird the way they worded that. But the interval needs to be widened. That's what they mean there, I guess. If they say to get a higher certainty, they're talking about to get a higher confidence interval than this. Even the interval would need to be wider. Okay. In a survey, people were asked whether they thought the sun went around planet Earth or vice versa. Of 1,877 people, 228 thought the sun went around the Earth, which that seems kind of hard to believe, right? That sounds kind of made up. Maybe it is. Anyway, that's what it says. So, what proportion believe the sun went around the Earth? 228 out of 1,877. 228 divided by 1,877 equals, may I have the envelope, please? 0.1215, okay? It wants 3 decimal places, 0.122. 0.122. Incorrect, doesn't like that. So what did I do there? 0.12, oh. Okay, I see. I see what happened. So the number I had, let me just to clarify here. When I did this on my calculator, I got 0.12147. Okay, now I'm not doing any other calculations with this number. It's just this number, all right? So I should just take that and round it to the number that they want. But I rounded it just to write it down to 0.1215, just in order to write it down. And then I was going to read what they wanted and round it again. And so I guess if it's just a single number, what I mean by that, a single calculation step, look and see how many they want and just do that rounding. Because I rounded to 4, wrote it down, which is 1215. Well, then I rounded that again, and I got 122, because I just looked at 1215 and rounded it. So that went to 122.122. But I should have looked back at the original long number, because this is just when we're not doing calculation steps, several of them. We're just doing a single step. So I should look at the original number with a whole bunch of digits, just round it one time, and I would have avoided that error. So live and learn. So just rounding that one time would be 0.121. Okay. 95% confidence interval is, let's do the confidence interval. Let's get it from Statcrunch, because that's pretty easy. So let me see if I can share this again. So proportion stats, 1 sample with summary, number of successes, 228, number of observations, 1877, confidence level, I wanted a 95% confidence interval, compute. So we get 0.1067 to 0.1362. Okay. And like that. Okay. Okay, to 3 decimal places, 0.107, 0.107 to 0.136. Is the scientist's claim that 20% of people in general population believe the sun goes around the earth plausible? Okay, so we look to see, does this fall inside our interval? Well, this is a percent, and we've got proportions up here, so we need to convert it. 20% we divide by 100, that gives us a proportion, okay? So 20 divided by 100 is 0.20. That's our proportion. And does 0.20 fit inside this interval? It does. So yes, it is plausible since the value 0.20, that's the proportion, is inside of the confidence interval. Check answer. Okay, what doesn't it like here? Is the scientist claim 20%? Oh, it's not in it. I read it too quick. Good grief. Okay, sorry about that. It won't let me edit that now. I don't know if you can see that anyway. Well, you can hear it. Anyway, the interval is 0.107 to 0.136. So the number is 0.20. And I just didn't look at that carefully enough. 0.20 is not inside that interval. So I need to, it won't let me, change that. Okay, I'll just go on. But so it would be no, it's not plausible because 0.20 is not in the interval. That's a silly mistake. See what happens if I do this. Okay. Oh, that's the last problem. That's 15 of 15. Okay, so we calculated the 95% interval, which is 0.107 to 0.136. Then there's a claim that 20% of the people, which the proportion from 20% would be 0.20. There's a claim that 0.20 is the proportion of the people that believe the sun goes around the earth. So you say, does 0.20 fit inside this interval, 0.107 to 0.136? No, it does not. And so it is not plausible since the value 0.20 is outside of the confidence interval. That's the end of the problem there. Little bump at the end, but I guess we're okay. So excuse me. I was just trying to think. I may make some other very short, I know this is a very long video here, but a lot of explanation. But all these problems are worked. You can fast forward through the different problems here and see what you want to see. I may put some very short videos on here before the final just to show you some other ideas, or well, we'll see. But anyway, this will be on Blackboard for your benefit. Have a great day. Have a good one. You got any questions, Levi? Are you still there? Are you still with me, Levi? Let's see. I apologize. I have to leave. Oh, okay. Levi's gone. Okay, signing out.